Hi, in this video we're going to talk about section 10.3, which is still polar coordinates, but we're going to be dealing with mostly polar curves or polar functions. Now, confusingly, or at least a little confusingly, remember that the coordinate is r comma theta. The only confusing thing is that usually the functions will look at r as a function of theta. So we saw a little bit of that in the last video. We would think about graphing theta first and then finding r. So usually what we're going to do is think about theta as the input causing some distance from the origin. So one way to think about this is we have a plane and we're going to be sweeping out around like a radar or like a lighthouse, and I'm going to be pinging how far I am at certain distances, how far an object is at certain distances, and we're just going to go around in a counterclockwise circle like this, recording at different places where we found a point. That's kind of the analogy. A lighthouse, a radar system, whatever works for you is fine. So let's try to graph r equals 2 sine theta. All right, so one thing I want to look at is that because of the period of sine, one idea might be like, okay, we're going to make a table, and I'm going to be thinking about theta as my input and r as my output. And again, this is backwards. This is a backwards kind of table. Theta is the input, but when we write the coordinates, it's r comma theta. And I'm just going to list the important angles from 0 to 2 pi. Sorry, 3 pi over 2 and 2 pi. So when I think about this, you should try to fill out the table. We're just going to plug in values for theta. Sine of 0 is 0. Sine of 2 pi is 1, so it's 2. Back to 0. Now at negative 2, and then ending at 0. So let's graph these points. So again, this is 0, 0. This is 2 comma pi over 2. Look how I flip them around. 0 comma pi. Negative 2 comma 3 pi over 2. And 0 comma 2 pi. So I'm going to be graphing them on an xy plane. This is why, again, with last lesson, you do not have to have polar graph paper to do a good job of this. Here's how we're going to do it. We have x, we have y. 0, 0 means the same in both languages. We're talking about the pole. Check. 2 comma pi over 2. So that's a rotation of pi over 2, getting me to the y-axis, the positive y-axis, any distance out by 2. Okay, check. 0 pi. So rotate pi, but don't go anywhere. So what we're talking about here, I guess I'll switch colors temporarily. We're talking about for this point, no, purple's going to show up. We're talking about here is the same polar point. It's the same literally at the pole. All right, then, we say, and we just keep trying to go. What about negative 2, 3 pi over 2? So 3 pi over 2 should have been a rotation that got us to here, the negative y-axis. But then instead of going that way, instead of going in the direction of 3 pi over 2, we're going to go backwards, which is 1, 2. So we're back here. And then again, Spoiler alert, 0, comma 2 pi is still the pole. In general, 0, comma theta is the pole. It's back to that same thing that we have infinitely many ways of representing a coordinate, and 0 is the only way of describing go nowhere from the pole. So there's infinitely many spots that refer to the origin. So we only have 2 spots here. Not a good strategy. Maybe you're cursing me for showing you this. Let's graph just a couple simple ones. Okay, let's graph pi over 6. If theta equals pi over 6, what's r equal? R is going to be 1. So that'd be a long pi over 6. I want to go, like, let's say that's pi over 6. I want to go 1 out, like here. And let's also graph, I'm just picking numbers that are easy. And in general, we're going to talk about what's happened here in a way that we'll never have to do all this again. 5 pi over 6. When I do 5 pi over 6, that's like this angle all the way over here. R would be positive 1. And you could graph more points like this. I'm not really that interested in doing it because at this point, I see what's happening. As I rotate, and you don't have to see it right now, hopefully we'll end up seeing together. As I rotate, 0 to pi over 6, and then there'd be pi over 3. Sorry, let's make it nicer. 0, pi over 6, pi over 4, pi over 3, back to pi over 2. And then we'd have, let's see if I can do it. 2 pi over 3, 3 pi over 4, 5 pi over 6, and then pi, we're back at the pole. Oh man, I can't, shaky hand. Ugh. You're gonna cheat. Oh no. Pi over 2, and then we're going to go 2 pi over 3, 3 pi over 4, 5 pi over 6, back to the origin. And so what we have here is a circle, or at least it looks a little bit like a circle. How can we find out? So in general, we're going to try to convert r equals 2 sine theta to rectangular coordinates. Okay. So the strategy I'm going to use here is try to get r squared. We don't have to do this a lot, but for this one it'll help multiply both sides by r. And what you would get is r squared equals 2r sine theta. And this is very helpful if you can't remember what I'm about to do or you don't understand what I'm about to do. You might want to watch the last video, or you might want to get your notes out and look at the polar conversion stuff. R squared is x squared plus y squared, right? It was the triangle law he had here. R, X, Y, right triangle. And similarly, R sine theta was 2y. I'm going to highlight this to be sure. R squared is x squared plus y squared, and R sine theta is the y. And then when you have an equation like this, you can always do what we call complete the square. And we're going to complete it for the y variable. It's half this number. It's half b. Squared goes here. So that's a positive 1. And I need to add it to both sides to keep things balanced. And what we have here is x squared plus y minus 1 squared equals 1. So this is the equation of a circle with radius equals 1 and centered at 0, 1. Let's go check if that's what we graphed. In terms of how I can draw, this is accurate. Here's the center, 0, 1, and it's a radius of 1 out. It was a radius of 1 to here, a radius of 1 to back to the origin, a radius of 1 back to the other y-intercept. So that's kind of the ins and outs of polar graphing. You want to graph a few coordinates and kind of get the general idea of a shape, and then picture again that radar sweeping around. I'm not expecting you to be able to do this perfectly. It'll take some practice. But I do want to point out a few things that might make it go smoother. It's our first kind of graph. We're going to discuss a lot of families of graphs. So we have, in general, R equals A sine theta, or R equals B, sorry, let's say A again, cosine theta, where A is a constant. Okay. A couple of things about these equations. They're always going to be circles, as long as you have A as a constant, and either sine or cosine, just with theta inside, okay? Always circles. The diameter is the absolute value of A. A can be negative. It doesn't change much. It's mostly just how it's rotating. That should sound right, whether you believe me or not, 100%. And then the centers on the y-axis for sine and the x-axis, let's say, or x-axis for cosine. Warning, the inside of sine or cosine is just theta. Okay, not 2 theta, not 3 theta. That's where we're going to see that. That's where we're going to see some other weird stuff happening. Okay? While we're on that note, we have, what if we have R equals a constant? This is just like a fixed, what did R stand for? Radius, which should give you an idea that these will always be circles centered at origin, the origin or the pole, with radius equals the constant, okay? Whatever the constant was. I mean, literally whatever number is here. That's the number that the radius will be. Should be clear? If you picture that polar graph paper, all the points with the r equal 3 away from the origin or the pole were those circles that were concentrically radiating out from the center. How about theta equals a constant? This is a pretty standard idea when we have new coordinate systems. So again, if we think of our xy axis, theta is a specific value away, and we'd have all these points going along that angle for positive radii, and all the points going opposite that angle for negative radii. So what do we get? These are lines through the origin. And it's one of the places where we get this notion that the theta, an angle, is kind of like a slope. It's a good measurement of slope. It does some of that for us. Okay. Let's go for the more complicated ones. So these three are all basic. You will need to know them. You will need to see them. You will be using them in the class. But more specifically, let's talk about r equals some weirder ones. R equals 1 plus cosine theta. And again, I'm going to graph using a table and choose values, the key values. Let's say key values 0, pi over 2. It's the same thing I did for the last problem. I swear this will work better. Why are these the values we choose? Because these are the values I would normally choose to graph cosine or to graph sine. If I know where these points occur, these are the maxes, the mins, and the zeros of cosine and sine. All right, so that's why this is really enough. I know that last one may have looked like a failure. It really is not. It's really going to be just okay. So what I want to do is theta, r, 0, pi over 2, pi, 3 pi over 2, and 2 pi. So what's happening here? When I plug in 0, I get 2. 1 plus 1. Back down to 1, because cosine of pi over 2 is 0. Down to 0 at pi, because cosine of pi is negative 1. Back up to 1, and then back up to 2, the former maximum greatness. So here's my xy plane. What's this graphing? Angle 0, go out 1, 2. Angle pi over 2, that's the positive y-axis, out 1. Angle pi, negative y-axis, don't go out at all. 3 pi over 2. And again, a positive radius means go in that direction. And then we're back to 2 pi. So again, I'm picturing a lighthouse. Picture a radar or a lighthouse in terms of revolving lighthouse in terms of revolving around. So we're starting from here. I'm revolving out. I know I need to hit this point. Sorry. I know I need to hit this point at an angle of right there, pi over 2. As I come back, I'm still trying to go circular. I notice I'm going to go back to the origin. It's going to create a cusp, actually. I have a specific name for this. Back out, down to 3 pi over 2. And then all the way back to start. So it should be a little rounder than that. But this kind of a shape is called a limaçon. Has a funny French, like cedilla or whatever. It's pronounced like an S. Specifically, this is a cardioid. And I'm going to point out cardioid right now because what it should look like is a heart shape, very roughly. And that's why it's called a cardioid, like a heart. So this is our second family of function, the limaçons. We have A plus B cosine theta, or A plus B sine theta. Okay. We're talking about A and B are constants. There's going to be a lot of stuff that happens here, depending on how their ratio goes. So, for instance, I'm going to have if A is less than B, we have an inner loop. So my example graph for this, and you should take a second to try to graph those same key points, 2 plus 3 cosine theta. So notice how B, the 3, is bigger than the 2. So graph those same key points, 0, pi over 2, pi, 3 pi over 2, and 2 pi. What do we have here? 3, 2, 1. I have a radius of 5, a radius of 2, a radius of -1. Uh-oh, that's the issue. This is the interesting part. Back to 2, back to 5. So what does this do? 1, 2, 3, 4, 5. Starts out way out here. When I get to pi over 2, I'm just out 2. When I'm at pi, instead of going this way toward pi, I'm going backwards. So the third point I hit, is here. That's what's going to cause the inner loop. I'm back. I'll draw this in a different color. This point is right here. That's what's causing me to double back the direction I just came from. Then back to 3 pi over 2, down here, and then all the way back to 5. So what do we got here? Again, rotating out, going for my first point. Check. This will actually go through the pole. Almost every single one of these will. So what happens is it goes through the pole. R will become 0. And then R is negative. And that's what's forcing it down here. The opposite direction of the angles we were supposed to have. We were supposed to be having angles in quadrant. Like this is quadrant 2. We were supposed to have angles in quadrant 2. And now instead we're having opposite direction in quadrant 4. Looped around. Now we're in quadrant 1 when we're supposed to be in quadrant 4. Again, I'm supposed to be here. The graph's not actually, so if that's confusing to you, Ignore it. Cover it up. And then we actually loop back around back to... Sorry, I'm going to try to make this symmetric. Back to that point. 3 pi over 2, 2. Sorry, 2 comma 3 pi over 2, really. And there we go. And that's what it looks like to have an inner loop. I'm going to shrink this down a bit. Just so it fits nicely. We have our cardioids. That's where A equals B. Cardioid. See previous. See last page. Slide or page. And we can have, obviously, the third case, A greater than B. And this will either be dimpled or convex. Like R equals 3 plus 2 cosine theta. Okay, so that's, things are reversed. I hope you see that. Same key points. And notice how, okay, the last one. Oh, no. Okay. The third case would be if A was greater than B, right? This would be what we call either a dimpled or a convex Limaçon. Let's look at R equals 3 plus 2 sine theta. The last two examples we did were cosine. And just like with circles, the cosine means we're going to be centered on the x-axis, whereas the sine means we're going to be oriented in the y direction, either up or down. So let's do theta and R one more time. 0, pi over 2, pi, 3 pi over 2. I'm just going to say this. When we're back to 2 pi for these shapes, we're going to be back where we started because that's the period. So it's enough just to check up to 2 pi. 0, we're going to get to 3. Pi over 2, now we're at our max. Pi, going to be back down to 3. And 3 pi over 2, we're at 1. Not at the pole. So for our cardioid, the key angle ended up at the pole. That's what makes this cusp happen. For this one, the max value went in. That's what made the inner loop happen. Here, the max value, and again, we're dealing with sine. That's why the max value is at 3 pi over 2. The max negative value, I'm sorry, I should have said the max negative value, the min value, the minimum value of sine. Gosh, all right, min. This is the min. This is the min. Undo what I was saying. This is the min. That's what makes these the key points of their respective functions. So, try to graph it yourself. Can you find these polar points? 3, 2, 1. So, 0, the angle, and 3 out along that angle. Check. Pi over 2. And 1, 2, 3, 4, 5. Did I trick you by having too small of coordinates? Because I tricked myself. Pi. In that direction. 1, 2, 3. And then 3 pi over 2, just 1. Again, we're going to rotate out, starting from 0, up to pi over 2, back down to pi, kind of look like an egg shape. And what's going to happen for this one is going to just barely get, this is what we would call dimpled. It's not going to be a cusp. It's not going to be as sharp as the cardioid, but it is going to be a dimple. This is dimpled. Convex would be no bump. And this one has a little bump. A former math teacher here at Mira Mesa used to call it butt functions. Like they look like butts. So you can enjoy that for whatever you want. All right. One last type of function, and then we can be done. Is something like r equals, I guess example still, 2 cosine 2 theta. So this is the first type where we notice the inside of the trig, is not just theta. Okay, what is that going to do? I want you to recall from pre-calc, the 2 theta changes period. What happens instead of the period is 2 pi, it's 2 pi over 2. So now the period is shorter. So just like we divide the period by 2, we're going to divide the key points. And see what happens. So what I'm saying is instead of 0, pi over 2, pi, 3 pi over 2, we're going to get 0, pi over 4, pi over 2, 3 pi over 4. And we might have to keep going until we have a clear picture. It's not going to be super straightforward always, but usually one period is enough. That should be the big takeaway from this video. If you learn nothing else, one period really should get me what I wanted. Pi over 2, 3 pi over 4. Because when I input these, I'm still getting the values that would maximize or minimize or make 0 this function. Okay. What I'm saying here, cosine of 0, still a max, getting 2. Instead of cosine of pi over 4, it'll be cosine of 2 pi over 4, 2 cosine 2 pi over 4. And what's 2 pi over 4? It's pi over 2. And what's cosine pi over 2? It's 0. Pi over 2, we're going to get negative. So we're going to have a output of negative 2. And 3 pi over 4 back to 0. So let's just graph that for now. I'm going to show you what happens. We're probably going to have to graph more. Hooray. 2, angle of 0. Angle of pi over 4. So pi over 4 splits this back. We're back at the pole. Okay, I'm just going to try to show you what's going on here. For pi over 2, we're not going to go too forward. We have to go in the reverse direction. So not toward pi over 2, but instead back down. And then at an angle of 3 pi over 4, which is actually this angle. I'm sorry. which is actually this angle, 3 pi over 4 is over here. It's late. We're going to go back to 0 yet again. Okay. I was thinking it is helpful to extend these, but that's not because it's 3 pi over 4. All right. So here we go. Rotating out, I follow this pathway in. It's really like going to be a tangent line. Spoiler alert. So where am I coming out? I'm coming out in this quadrant 3. Because again, now my angles are all opposite. Sorry, my radii are all opposite of what I wanted. And I'm looping back around. And then back in. It's actually going to get pretty symmetric here. So let's keep going by pi's over 4. I'll do some more rotations. So let's do 4 pi over 4 is back to pi. 5 pi over 4. At pi, it's really cosine 2 pi. So back to 2. And 5 pi over 4 would be back to 0. So this is the pi direction at 2. And then back to 0 one more time. So when we last left off, we were at 3 pi over 4, coming back down to the origin. And now I'm going to keep going. I'm going to loop around one more time. And you can graph more points. You should test it out and see what these angles are going to. You would get another repetition at, where would we be at? 6 pi over 4. You get negative 2. I'll write it out then. 6 pi over 4, which is 3 pi over 2. We'd have r equals negative 2. And that's what puts us up here again. Looping back around. Looping one more time. It should be more symmetric. They should be same size petals. I'm writing it down because I'm not going to graph it again. But same size petals was the goal. And I know I failed at that. But as long as you try to emphasize it, I'll give you the credit too. So what do we call these? These are the roses. So polar can create some pretty shapes. And just to go back really quick, what I had said at the beginning of the last video was that polars are useful for graphing circular shapes. This is what I mean. A circular shape that you would never in a million years decide to try to graph in rectangular. If you try to solve this in rectangular, it's very, very difficult. Even something like a limaçon is much more straightforward to solve, but still very clearly not a function, and not really this kind of rounded shape that we were ever talking about before. But we will have polar graphs like a rose, and here's the idea. So it's going to be r equals a cosine n theta, or r equals a sine n theta. And what a will do is going to be the max length of r, I guess absolute value of a, just to be clear, which is the same as the length of a petal. If b is even, sorry, not b, ugh, my notes are different. If n is odd, we'd have, I completely changed it. We'd have n petals. You didn't see that graph. I'll do one like this in a second. If n is even, we'd have 2n petals. So this is what we saw in the last example. I guess I should put bullets for this list. Okay, we had 2 theta. We had 4 petals. So I'll do the second bullet point really quick here. If I had r equals 4 sine 3 theta. Now the sine's really going to do something a little weirder. it is going to make one of the petals lie along the y-axis. But in general, when we have these kinds of petal shapes, we are going to have some weirdness going on. They're not all going to line up on axes like they did nicely here. It's just that we have 4 axes, we have 4 petals, they are going to line up somewhat nicely. So notice my key values. I'm going to divide by 3. And again, this is what I said on the last slide. We had 2 theta. Oh no. We had, oh my gosh, 2 theta. So we divided by 2 for the period. That's the stuff I'm talking about. So I'm going to have 0. Instead of pi over 2, talking about pi over 6. Instead of pi, talking about pi over 3. Instead of 3 pi over 2, talk about pi over 2. And we could keep going if we wanted to, but this is enough to give me one of the petals truly. Okay, so we'd have 0, 4, back to 0, and then negative 4. So what are we talking about? 0, 0. Along the angle of pi over 6. I'm trying to go 1, 2, 3, 4. Okay, some distance along there. Along the angle of pi over 3, back to 0. And then along the angle of pi over 2, up to 1, 2, 3, 4. What the heck's going on, right? So starting from 0, rotating out to there, back to 0. Sorry, so it needs to be a little bit wider to be symmetrical. Okay. Back to 0 along the line pi over 3. So what's going on here? We'll start with graphing 0, 0. And then along the line pi over 6, which is like a third of this quadrant, I'm counting 1, 2, 3, 4. Like literally just trying to give an approximation of what it looks to be 4 along that direction. By the time we get to pi over 3, we're going to go back to 0, the pole. And then pi over 2 would be this direction. But I have a negative 4. So instead of going that direction, I'm going backwards. 1, 2, 3, 4. So here we go. Out along angles, rotating until I get to that point. And we're just going to keep trying to rotate it. Back to the origin, trying to go along that angle. And then back down here to this. And if you try to think about symmetry and how we have one more petal to make, this is going to loop back around. You could graph more points if you wanted to be sure. And then we're going to come out at an angle of pi over 3, reach an apex of 4. I'm going to try to do my best job of this without sketching it nice. And then come back at an angle of pi over 6. Probably could have gone out further, huh? That's good enough for government work. Okay. Poop. So that's the rough cuts. Try out the homework problems. Try to graph a few of them. Use this as a guide to see what they should look like. have fun, and I'll see you in the next one. Bye for now.